Hi guys, so in this video we're going to be taking a look at an initial value problem which involves using case study 2 to find an integrating factor to solve a differential equation. So here goes the question. So we're asked to use case study 1 or 2 to find an integrating factor and after finding the integrating factor we are required to solve the given differential equation. And differential equation is an initial value problem e raised to the power of x plus y plus y e raised to the power of y dx plus x e raised to the power of y minus 1 dy is equal to 0. And the initial conditions we are given is that the value of y when x is equal to 0 is minus 1. So we've seen something similar to this expression, so I don't think it should be strange to any one of us. So to solve this, since we have been told to find an integrating factor, we know that it is not an exact differential equation, but that shouldn't still stop you from solving and checking if it's an exact differential equation or not. So in this case, we are going to test for non-exactness, just to be double sure. So from here, we have that our p is equal to e raised to the power of x plus y e raised to the power of y, and q is x e raised to the power of y minus 1. So we need to evaluate the p dy, that is the partial derivative of p with respect to y, and that's going to give us e raised to the power of x plus y plus, for the second time, we are going to be using product rule, so that becomes plus e raised to the power of y plus y e raised to the power of y. So we can go ahead to factorize this as e raised to the power of y into brackets e raised to the power of x plus y plus 1. So this confirms the p dy. We now need to evaluate the q dx. So I'll write what q is here. Q is equal to x e raised to the power of y minus 1. So the q dx now becomes e raised to the power of y. So you can see that our dp dy, which we got, is not the same thing as the q dx. So this confirms that the differential equation is inexact. So we now need to solve for the integrating factor. In solving for the integrating factor, let's examine case study 1 to start with. So for case study 1, we have the p dy minus the q dx divided by p. We are trying to evaluate this r. So recall that from what we solved, we know that our dp dy is e raised to the power of y into brackets e raised to the power x plus y plus 1 minus the q dx is e raised to the power of y divided by p is given to be e raised to the power of x plus y e raised to the power of y. So let's try to simplify this. We now have this as e raised to the power of x plus y e raised to the power of y plus e raised to the power of y minus e raised to the power of y divided by, okay, sorry, I think is divided by q in this case, not divided by p. So if it's divided by q, the denominator changes. So we divided by q. We have q to be x e raised to the power of y minus 1. So this becomes divided by x e raised to the power of y minus 1. So simplifying, we have this to become x e raised by x plus y e raised to the power of y divided by x e raised to the power of y minus 1. So it is clear that this can't be further simplified, and this is a function in x and y. So this is a function of two variables, and that's what we are avoiding. We either want the result to be a function in x or a function in y only. So let's try to examine case study 2, since case study 1 has failed. So in examining case study 2, we are looking for r, which is equal to the q dx minus the p dy divided by p. So in this case, our dq dx is e raised to the power of y minus our dp dy is e raised to the power of y into brackets e raised to the power of x plus y plus 1. So you can then divide this through by p, which is e raised to the power x plus y e raised to the power of y. So on simplification, we have e raised to the power of y minus e raised to the power of x plus y minus y e raised to the power of y minus e raised to the power of y divided by e raised to the power of x plus y e raised to the power of y. So by collecting like terms and simplifying, we have that r is equal to minus e raised to the power of x plus y minus y e raised to the power of y divided by e raised to the power of x plus y e raised to the power of y. So this becomes minus into brackets e raised to the power of x plus y e raised to the power of y divided by e raised to the power of x plus y e raised to the power of y. So this becomes minus 1. So you can see now that could r could be said to be equal to a function in y only, which is equal to minus 1. So it means case 2 holds. And recall that we said if r is equal to ry, our integrating factor is going to be equal to e raised to the power of integral of ry dy. So this becomes e raised to the power of the integral of minus 1 dy. This becomes e raised to the power minus integral of dy. So our integrating factor gives us e raised to the power of minus y. So this is the required integrating factor, and we've completed the first part of the question, which asks us to find the integrating factor that is necessary to solve that differential equation or the initial value problem that's been given to us. We now need to formulate the new differential equation. And how do we do that? We simply multiply the inexact differential equation that we have been given by the integrating factor that we've calculated to obtain our new equation. So the original equation we had been given is e raised to the power of x plus y e raised to the power of y dx plus x e raised to the power of y minus 1 dy. Then we multiply this by e raised to the power of minus y, which is our integrating factor, to give us 0. So by expanding the brackets, we have e raised to the power of minus y into brackets e raised to the power of x plus y e raised to the power of y dx plus e raised to the power of minus y into brackets x e raised to the power of y minus 1 dy should be equal to 0. So we can further simplify this to become e raised to the power x plus y multiplied by e raised to the power minus y plus y e raised to the power of y multiplied by e raised to the power minus y dx plus x e raised to the power of y multiplied by e raised to the power minus y minus e raised to the power minus y dy is equal to 0. So we can simplify this using our laws of indices. So we have this to become e raised to the power of x plus y dx plus x minus e raised to the power minus y dy is equal to 0. So this is the new differential equation that we've obtained by multiplying the original differential equation by the integrating factor. So we have to test for exactness of this new differential equation. We have to test for exactness. This is a very vital step. So the differential equation is e raised to the power x plus y dx plus x minus e raised to the power minus y dy is equal to 0. So you can compare this with m dx plus n dy to be equal to 0. So we know that m is equal to e raised to the power of x plus y and n is equal to x minus e raised to the power of minus y. So dm dy is going to be equal to 1 and dn dx is also equal to 1. Therefore, dm dy is the same thing as dn dx, which is equal to 1. So this confirms that the given equation is an exact differential equation. So after doing that, we need to obtain the general solution. Recall in the last video, I said we could fuse steps 2 and 3 together as a single step. So that's what we are going to be doing here. The general solution is of the form integral of m with respect to x plus the integral of the terms of n that doesn't contain x with respect to y, and this becomes a constant. So z now becomes integral of e raised to the power of x plus y with respect to x plus integral of x minus 0 raised to the power minus y. Oh, sorry. We said the terms in n not containing x. So from this, we can see that the terms of n that doesn't contain x is just minus e raised to the power minus y. So this becomes minus e raised to power minus y dy. So this is equal to c. We can now integrate both sides, the expression. So we have this to be e raised to power x plus xy plus minus e raised to power minus y divided by minus 1 is equal to c. So we have that z is equal to e raised to power of x plus xy plus e raised to power of minus y, and this is equal to c. So this gives the general solution of the differential equation. But since it's an initial value problem, we have to find the particular solution for the differential equation. So the general solution, say GS, is given as Z is equal to e raised to the power of x plus xy plus e raised to the power of minus y, which is equal to c. And we're given the initial conditions as y0 is equal to minus 1. Let's call this equation 1. So we can substitute x is equal to 0 and y is equal to minus 1 in equation 1 to get the value of c. So in doing that, we have e raised to the power of 0 plus 0 plus e raised to the power of minus 1 is equal to c. So we have that c is equal to 1 plus e raised to the power minus 1. Sorry, y is minus 1. So this is minus 1. So this plus 1 instead, which is equal to 1 plus e. So in evaluating this in your calculator, you have that c is equal to 3.1783. If you punch it into your calculator, please ensure that you get the same results from your evaluations. So therefore, the particular solution of the differential equation is given as z is equal to e raised to the power of x plus xy plus e raised to the power of minus y, which is equal to 3.7183. So yeah, I wrote 1783. Pardon me, please. So this should be 7183. So this is the solution of the differential equation. So with this, we've come to the end of the series on exact differential equations. Thank you very much for watching this video, and I hope you enjoyed it. See you in the next video.